Okay, so let me return to where I left off yesterday. So basically, I started describing a bit of this infinitesimal global correspondences. So I talked about Lie bialgebras, and I gave an alternative point of view to them in terms of objects known as money in triples. So basically, the way to find Lie bialgebras, or a natural way, is to look for quadratic Lie algebras and to subalgebras which are Lagrangian in there, so that the direct sum as vector spaces is the whole thing. And then I discussed a bit Lie algebroids, which are the infinitesimal counterparts of Lie groupoids, and I mentioned a few things about examples and things like that. So one thing that I forgot to say, and I think Yvette reminded me, that I meant to assign a little exercise, which is just that if you have a Lie algebroid, so remember that basically this is a Lie bracket on the space of sections of this vector bundle, and this was some bundle map from A into Tm, and these two things were related by the Leibniz identity. So the exercise is to show that the map rho going from sections to vector fields at the level of sections, this is bracket preserving. So this follows from the Leibniz identity. Okay, and then I also start discussing a bit the connection between, describing a bit the infinitesimal counterpart of symplectic groupoids. Here. And so the theorem that I discussed was that on the one hand, if you have a symplectic groupoid, remember that in the case of a symplectic groupoid, so you have a groupoid which has a symplectic form. So in principle, you have two algebroids in the picture. One is just the Lie algebroid of the groupoid itself, and the other one is the Lie algebroid associated with the Poisson structure that the base of the groupoid naturally inherits from the symplectic form. Right? So there's another Lie algebroid here. So the first observation was that these two algebroids on a symplectic groupoid, they are isomorphic. Okay, so I gave you the map for that. So basically, it's the first statement in the theorem there, is that if you have a symplectic groupoid, then the symplectic groupoid always integrates the Lie algebroid of the base Poisson manifold. Okay, and then the other statement was a kind of converse to that, which is that if you know a groupoid, a source simply connected groupoid, integrating this algebroid, then it's automatically symplectic. It is a symplectic groupoid. So basically, one way to understand this result was discussed by Rui this morning. So there is a certain infinite dimensional reduction in terms of path spaces that will realize the symplectic groupoid, the groupoid integrating this. And because it's a symplectic reduction, even though it's in infinite dimensions, the symplectic form on the groupoid comes from that. That's one point of view. I will mention another way, purely finite dimensional, to explain why the source simply connected groupoid integrating this is symplectic. Okay, without using these path spaces. And here, perhaps another exercise, very simple. It's just a remark, which is that the theorem says that the source simply connected groupoid integrating this algebroid coming from a Poisson manifold is symplectic. But it's not saying anything about other possible groupoids. Okay? And in fact, this is a simple example. So if you consider the sphere S3 with the zero Poisson structure, then certainly, so one groupoid integrating it, actually the source simply connected one, is just the cotangent bundle of the sphere. And the groupoid structure, as I said, is just, just view this as a vector bundle. Any vector bundle is a groupoid. in which source and target are just the same map, the projection map, and the groupoid operation is just the fiber-wise addition. Right? So this is the symplectic groupoid associated with this. But this guy is trivial as a bundle, right? And there is another groupoid that you can come up with integrating this, which is S3 times T3. So here, the groupoid operation is just, again, the fiber-wise, so this is just the projection onto the first factor, and the groupoid operation is just the torus operation fiber-wise. Right? So this is, again, a groupoid integrating the same algebroid here, that is the algebroid coming from the Poisson structure. But this one, even though it's a Lie groupoid integrating it, is not symplectic. It does not carry any symplectic. So the exercise is to understand why. Okay, so just a small remark. So I want to go down on my list, and there was another object that I defined, I think in my, maybe yesterday, which was Poisson groupoids. And right, so far we have, this infinitesimal global correspondence for Lie bialgebras or Manning triples and Poisson Lie groups, Poisson manifolds that you can view as infinitesimal objects through Lie algebroids and symplectic groupoids. And I spoke about Poisson groupoids, and I would like to say a few words about their infinitesimal counterpart, just to complete the picture. Okay, and then we see, and some interesting geometrical structures will appear in this context already. Okay, so here's an outline of the lecture. So basically I will introduce these objects known as Lie bialgebroids. I'll talk about their doubles, and maybe I'll give an idea of the proof of all these infinitesimal global correspondences. At least like one technique to prove these results. Okay, so now I'll mostly, follow an analogy to define these bialgebroids with bialgebras, right? So remember that, basically I'm extending this concept of a Lie bialgebra, in which I had a Lie algebra, and the dual also had a Lie algebra structure. And if you see the Lie algebra structure on the dual as defined by the corresponding Lie algebra operator on exterior powers of G, then this operator is a derivation of the Lie brackets. That's the compatibility condition. So here's a definition. Well, I shouldn't leave this here because it won't be about this. So here's a definition, a more general definition. So suppose that you have a Lie algebroid now. So here the bracket and the anchor. So I'll say that the pair A and the dual bundle A star is a Lie bialgebroid. If A star has a Lie algebroid, is a Lie algebroid itself, right? So the structure for A star, I think I'll denote by, so the anchor like this, and the bracket on sections of A star like this. But recall, so this is just some notation, but recall that this can all be encoded on an operator that now acts on the dual of the dual, which is again A. So it's an operator that satisfies Leibniz with respect to the wedge product and squares to 0. That's a Jacobi identity, right? So it's the same thing, giving you this or this. I gave you the formulas last time, and the compatibility condition It's just that this operator is compatible with the bracket. Okay, just as before. Just write it like this. Where here I'm taking U and V as sections of A. I can also extend this compatibility to other sections putting the appropriate sign, but this suffices. Yeah?
Is there a relation that you can state in terms of DA and DA star instead of using D and a bracket?
Well, but they live in different places. You have to dualize one of them so that they live in the same place so that you can write a compatibility equation, right? Because so DA star, so the complex is wedges of A, and DA, the complex is wedges of A star. So you have to dualize one.
But is there a symmetry like in the case of...
Yeah, sure. Yeah, I'll get to that.
You need to extend to wedge A first because DA star of U is no longer...
Right. So yeah, so I'm implicitly here, just what I said before yesterday, that I will always see Lie algebras or Lie algebroids either in terms of the skeleton brackets on sections or the differential, and I will go freely from one point of view to the other. So yeah, so this already involves a certain extension of the Lie bracket on sections to wedges of sections. And there's a natural way to do it. Okay, so some examples. So certainly, if A is a Lie algebra, then we are just back to Lie bialgebras. So it's just straightforward to check that. And another example that will be relevant is if you have again, right, so in the same way that Poisson groupoids had as extreme examples Poisson Lie groups and symplectic groupoids, their infinitesimal counterparts should include, on the one hand, Lie bialgebras, on the other hand, Poisson manifolds. Right? So how do you see a Poisson manifold as a Lie bialgebroid? So here you have this algebroid associated with the Poisson structure, and you have just Tm with the canonical Lie algebroid structure that it has, just in terms of the bracket of vector fields. So you can look at either, what I want to do first. So, right, I mean, either this pair I claim is a bialgebroid, and also this pair will naturally be a bialgebroid, and it is in fact true, even though my definition in principle is not symmetric in A and A star. You know, in a little bit we'll see that this is really a symmetric relation in A and A star, right? So I'm explicitly showing that here and here. So I have to tell you what the operator associated with the Lie algebroid structure here, you know, what it is here, right? So in this case, so what is the operator associated with the canonical Lie algebroid structure on Tm? So this is an operator on T star, wedges of T star of M. There is to say forms. So how many of these degree 1 operators do you know on forms? First guess? First guess? Right. So this is just the Deram. So that's what this operator is. And you should check in principle that it's compatible with the skeleton bracket on multi-vector fields, but it is. And now I need an operator that is defined on wedge products of this, which are multi-vector fields, given that I have a Poisson structure around. Right? So there is a natural guess for that too. So in this case, if this is A and this is A star, this is just the Poisson, just Litvinovich Poisson cohomology operator that Rui talked about. Right. Okay, so what the infinitesimal global theorem in this context now is this. So suppose again that you have a Lie groupoid that is source simply connected, and take A to be its Lie algebroid. And the theorem is that there is a one-to-one correspondence between multiplicative Poisson structures on the Lie groupoid, there is to say Poisson groupoid structures, and Lie bialgebroids, there is to say, operators like this on the Lie algebroid of the groupoid. Okay? So here is how you do that, at least in the easy direction. I'm going to tell you how you extract the Lie algebroid structure on the dual of the Lie algebroid of G directly from the bivector, from the multiplicative bivector. And this is kind of similar to what we did in the Poisson Lie group case. So these are the formulas. So what is this saying? So here, I can erase this. So what is this saying? So here, what you have to notice is that from the multiplicativity condition, again, this was defined in terms of the graph of the multiplication being coisotropic on the triple product of the Lie groupoid with one sign in the end, that you have this property. So basically, if you contract a multiplicative bivector field with something like this, that is the pullback by the target of a one form on the base, then you get, so the result of this is a vector field on the groupoid. And the multiplicativity will say that this combination will give you something that is right invariant. So if it's right invariant, it comes from a section of the algebroid. Remember that section of the algebroid were identified with right invariant vector fields by right translation, right? So this really gives me a map. How am I calling it? I put 0 here because it's in degree 0. That takes functions to sections just by this equation. This. So this gives me a map. And the other property that a multiplicative bivector field has is that if you take its Lie derivative with respect to a right invariant vector field, right? Now the result is a bivector field again. And the multiplicativity now will imply that this new bivector field is right invariant. Okay? So this gives me an operation that takes a section, which was the input here, and produces a section now of wedge 2 of A, which is what I'm going to put here. Okay? Now I have an operator defined here in degree 0, degree 1 to degree 2. I extend it using Leibniz, right? Then you have to check that, in the same way as before, that the integrability condition of the bivector on the groupoid implies that the square of this operator is 0. That's what guarantees that it is a Lie algebroid. And there is still the compatibility given by that equation on the other blackboard. And that's also easy to derive. You just look at this formula. You substitute this by, you want to know what happens, when you put here the bracket of U and V. But you have this formula, so you just replace it by the bracket of U and V here. You expand this out, and you see what comes out. It's exactly that compatibility there. Okay, so that's what proves at least the easy part, which is going from global to infinitesimal. Of course, the harder part is to go back, is to know that just this data is enough for you to recover the global object. Okay, and I'll say a few words about this towards the end. So one thing that I want to mention is that, in the case of... Is this on? Oh no, sorry. So in the case of Lie algebras, there was this other point of view to Lie algebras based on money in triples. Right? So the first thing, which was, kind of one way to see that the definition of a Lie algebra was symmetric in G and G star, what we did there was first to consider this double. So we added so recall that for Lie algebras, it was kind of a nice point of view to first consider its direct sum with the natural symmetric pairing that you have there. And we saw that there was a certain bracket that you could put on this direct sum. To write down the bracket, all you need is a Lie algebra structure here. Well, a bracket here and a bracket here. A Lie algebra structure here and a Lie algebra structure here. And you can write a certain bracket with a formula. And the nice thing was that, the compatibility between the two Lie algebra structures was equivalent to the Jacobi identity for this bracket on this direct sum. And this was called the double. So you get a new, bigger quadratic Lie algebra. Right? And then I also mentioned that this thing also goes the other way. So whenever you have a Lie algebra that as a vector space, you can write a Lie algebra with an adding variant scalar product, so that you can write it as a direct sum, as a vector space of two isotropic, if you want, subspaces which are subalgebras. Then you are in this situation again. Right? That was like what a money triple was. So we can try to play the same game for Lie algebroids now and see what we get. So suppose now that you have, so here is one algebroid, here's the other algebroid. Now you have these anchors, right? It's not only about brackets. And then you can take, a vector bundle now, right? So this is a vector bundle over M. This is a vector bundle over M. So you can take this direct sum, right? As soon as you do that, you have this pairing around, right? Just to be totally explicit, this pairing is something like this. Okay, so you have this pairing around, and you can try to come up with an anchor, some kind of map from E to Tm, from what you have there, from your data, and there's nothing more natural than just, I guess, adding them up, right? And then you can wonder, okay, can I find a bracket? Can I find a bracket here with the same property that this bracket here, in the case of Lie algebras, had? Somehow, encoding the compatibility in terms of some condition on this bracket. Ideally, Jacobi identity, just to be totally analogous. So here is a possible. So this is a possible bracket. This is a possible bracket that you can write on the direct sum of A and A star. So you see, you write this formula and you see right away, it's very simple to see that this in fact, this really generalizes the formula for algebra. Right? There are other ways to write it, but this is one way to write it. A generalization. And then it would like, let's say, using this bracket, to prove a theorem of the type, A and A star. To write this bracket, I only need the Lie algebroid structures on A and A star. So is there any way that I could encode this compatibility condition in terms of this object that I'm producing being, I don't know, some property of this bracket? And if this was just a game of words, right, then you would guess something very naturally. So in this case, you had a Lie algebra, and then you had another Lie algebra. You put them together, and this bracket is a Lie algebra bracket here. So then the natural guess would be, which is compatible with this inner product. So the natural guess here would be, I guess, that if you have now, a Lie algebroid, another Lie algebroid, you put these things together, you have, all the ingredients to have a Lie algebroid again, except that you still have a bracket around, as you had here. But unfortunately, this doesn't work. And the resulting object of this operation is not a Lie algebroid again. And so doing this double story, forces you to fall out of the world of Lie algebroids. So, whenever you find a new object, you kind of try to axiomatize it and try to understand what the object is. So that's what was done by Liu, Shu, and Weinstein. Now I think we are around maybe mid-90s, like 96, 97. I'm not sure. So they managed to axiomatize, the bracket that resulted from combining combining a bialgebroid into one thing. So these are the some of the axioms, right? So the first axiom looks kind of nice. It's some kind of Jacobi-like identity. The second axiom is a Leibniz condition, which is kind of nice too. The third axiom is a very natural compatibility between the pairing and the bracket, some kind of adding variance, if you want. And the fourth is just the property that was an exercise that I asked you to check in the beginning of the lecture. So it's also very natural for if you wanted to have a Lie algebroid. But then, the way I wrote things, there's an extra axiom that spoils everything, which is something that prevents this bracket from being skew symmetric. Okay, so the bracket is not skew symmetric, the way I wrote it at least. Originally, the bracket was written in a skew symmetric form, and then all these conditions were kind of had anomalies. The Jacobi identity had an anomaly, the Leibniz had an anomaly. I just rewrote things in a convenient way, just another way to express the same object that looks a little nicer in terms of axioms. Okay, so this is the axiomatization of the object that you get, and this is what is called a current algebroid. And current algebroids are objects of interest in Poisson geometry, and there will be talks I think next week. Like Raj will be talking about current algebroids for sure next week, and perhaps more people. And let me just say a few things about a few observations about what we can say from the axioms. So here are some simple observations that will be relevant. So observation number one. So if you have a subbundle of E, with the structure there, which is isotropic. By that I just mean that the pairing on this subbundle, on sections of this subbundle, on this subbundle, is 0. And which is involutive with respect to this bracket, then the resulting object, if you restrict everything to it, is a Lie algebroid. So even though the object itself is not a Lie algebroid, it has many sub-objects which are Lie algebroids. And that's very easy to check, just because once you restrict yourself to a sub-bundle that is isotropic, then this problem with skew symmetry goes away. Right? I mean, like the pairing there would be 0, so then you would get really something skew symmetric. And then you have the other axioms of a Lie algebroid already there. Right? So that's an important observation. And the other observation is that for the case of E being produced out of a bialgebroid, right, so it's one of these objects, then both A and A star sit inside E as so they are both Lagrangian, and what I mean here by Lagrangian subbundles of E are just subbundles which are isotropic and which have half the dimension of E, if you want. So they are Lagrangian subbundles. And involutive. Right, that's how A and A star, and therefore, and the Lie algebroid structure that each one has is really inherited from the big one in this way, just by restriction. Okay, so this motivates the following definition. So if you have a current algebroid, and if you have, I guess, a Lagrangian subbundle that is involutive, this is called a Dirac structure. Okay, and the result here. Okay, so so the result here then is right. And then, given that, I can define now, just in total analogy to what I had before, a current algebroid with a pair of Dirac structures which are transversal to each other. This is exactly the analog of a Manning triple, and I'll just call it a Manning triple again, because triploid is something that I just refuse to say. So it's just a Manning triple. What? Manninoid, no. So it's just a Manning triple again. I'll just use the same name. Right, so this is what a Manning triple is, and the result is... Yeah.
Currently, for Manning triples or for Lie algebras, there is also a quantization problem. Is this a well-defined quantization problem in this setting to some kind of whatever pop?
Yeah.
So there is.
Yeah. Right. Yes. Quantum groupoids and algebra. Yeah.
In the definition of the current algebroid, are you assuming that this bilinear form is split signature, or?
Right. So in principle, I don't really have to assume that. So if I don't assume that, then maybe these pairs of transversal Dirac structures will not exist. But if you want them to exist, then I think that you should assume that that the signature of the pairing is split. right? So it's implicit that, you know, if you have a Manning triple, then certainly you need this property of the pairing, right?
Is non-degenerate.
Right, and the pairing is non-degenerate, right? Yeah, so it's symmetric, non-degenerate pairing, scalar product.
What about the dual of E? Is there some property like biology?
Oh, that's a good question. Does anyone know that? The dual of E, if it inherits anything reasonable. Where's Dima?
It's pretty easy to see. Because case is given by biology, but if you don't, you
Yeah,
cannot see.
right, yeah, I don't know what it is. Yeah, I don't know what it is.
It is the same object. It is somehow self-removed. It is somehow A plus A star.
Yeah, in general, I just don't know what it would be. Yeah, maybe it is. I just don't know. Okay, so, and the theorem in this case is that really, you know, Lie algebroids can be equivalently seen as these generalized Manning triples, where now you have a big thing which is a current algebroid with those axioms, and you find in there two involutive Lagrangian subbundles, which are called Dirac structures, which are transversal to each other. Right? So let's see. You know, just like for Lie algebras, you know, in general, I mean, this is I think a more natural way to find bialgebroids, you know, in nature, so to say, in math. I don't know. So let me give you some examples. And in particular here, you know, it becomes clear with this equivalence that it is a symmetric definition on A and A star. Okay, so let me talk about a couple of examples. Okay. Well, certainly I should, you know, I'll just say it, but in this case, you know, their double is just the usual double. Right? So in particular, yeah, so you know, a current algebroid over a point is nothing but a Lie algebra with an ad-invariant inner product, right? So as Rayer mentioned, if this ad-invariant inner product has split signature, then you may be able to find Lagrangian subspaces, and if we're even luckier, then you may be able to find involutive or, you know, subalgebras like that. Okay, so here, you know, you really just recover this theory when you are over a point. Now, something different is this. So let's suppose that now we have a manifold, and let's choose just the zero Poisson structure in this manifold. So certainly, Tm is a Lie algebroid. T star m is also a Lie algebroid, where now I put the zero Poisson structure, so you know it's a totally trivial Lie algebroid. So it's zero anchor, zero bracket, everything is zero. Okay, but this is a bialgebroid. So let's take the double and, you know, follow the formula. So if you do that, then the bracket that comes out, so my notation is something that looks like this. So in the first component is just, right, so here I'm talking about, it's a bracket on section, so you know this is a vector field, one form. So at the vector field part is just the usual Lie bracket of vector fields, and on the one form part you get the following combination. No, here's, sorry. So that's what you get. And this is the so-called Courant-Dorfman or Dorfman bracket. So basically, this bracket appeared in the work of Dorfman, and a skew-symmetrized version of this bracket appeared in the work of Ted Courant, and in the context basically of mechanics, of constrained mechanics, and the study of objects known as Dirac structures that were first defined in this setting for this particular Courant algebroid. So here you have the usual pairing, and this anchor is just the projection onto the first factor. Okay? So this is another double that gives rise to an object that is quite important. So this object, this particular Courant algebroid, plays a very important role, for example, in generalized complex geometry, that I think there will be talks about it next week, I guess. Good. So as I said, I'm just taking the opportunity to speak about a bunch of things that appear in this business of going infinitesimal and global. Right? So, so here's just a little summary of what we have so far. So, on the infinitesimal side, you have Lie algebras. On the global side, Poisson-Lie groups. And then if you go to Groupoids and put symplectic structures, you get Poisson manifolds. You go to Poisson Groupoids, you get this geometry that is basically given by a Courant algebroid and two Dirac structures which are transversal in them. So you naturally get them just by playing this game. Okay? And so let me just say, I think I have time. Let me just say a few words about, just say a few more things about, this particular Courant algebroid. Just giving it a few more examples of objects there. Okay. So one observation is that you have many interesting examples in this particular Courant algebroid. So this one that I was talking about. So again, Dirac structures are Lagrangian subbundles with respect to the pairing in here, which are evolutive with respect to this bracket. So some examples are so just to mention. So first of all, you can represent two forms on the manifold in terms of Lagrangian subbundles here, just by looking at the map that they define by contraction, and then looking at the graph of this map inside T m plus T star m. And in this case, the involutivity condition with respect to the Courant bracket amounts to the two form being closed. So another example is if you do the same thing now with closed two forms. There's no they don't have to be non-degenerate. So another object would be if you take a bivector field, like the dual object on the manifold, and then you have this map that we already saw many times. So just the map that takes, basically functions to Hamiltonian vector fields, like this. And then in this case, you can look at the graph again as a Lagrangian subbundle. And then the integrability condition is exactly that. This is a Poisson structure. So, it's a very convenient way to describe lots of geometrical structures. And there's a way to include complex structures in this picture as well. And that's what these generalized complex structures are about. Just to give you one more example that is classical too, if you have any subbundle of Tm, you can promote it to a Lagrangian subbundle of Tm plus T star m by looking at F plus its annihilator inside T plus T star of m. And in this case, the integrability condition, the involutivity condition of this wannabe Dirac structure with respect to the Courant bracket is that the subbundle is involutive with respect to the Lie bracket. So it's tangent to a foliation. Okay, so these are all natural kinds of geometries that appear as Lagrangian subbundles of this particular Courant algebroid. So, the examples of, so in particular, if you're looking for Manning pairs, or Manning triples, I'm sorry. So if you're looking for Manning triples, so you need pairs of transversal Dirac structures. So for example, so if you have here T and T star, and you have a Poisson structure, right? So I can view it in terms of its graph, and we saw that this is a Dirac structure, right? Now, because this is a graph from here to here, this is also a Dirac structure, they are transversal to each other. So this pair defines a Lie bialgebroid. Okay, and this is nothing but, it's the same Lie bialgebroid that I talked about before. Okay, so a different way to see the same thing. All right. So, how much time do I have? 10 minutes. So let me say a few words about this global infinitesimal. So again, about these correspondences and how to prove them, or one way or some ingredients in the proof of these results. Okay. So ingredients for proofs. So one way that you could approach the integration part, right? So I just, all this time I just told you how to go from global to infinitesimal doing some tricks, but let me try to say a few words about how to go back. And so the first ingredient is, I think, really goes back to Mackenzie and his, he found a different way to understand multiplicativity. So let me just remind you that for forms, right? You have forms and bivectors there, but for forms, we had a nice equation for what multiplicativity was. and I'll talk more about this equation tomorrow when I talk about forms in general, it even has some kind of cohomological meaning. Right? There was an equation like this. And for bivectors, bivector fields, in the case of Lie groups, there was also some kind of equation that you could write, which was equivalent, which was something like this. But already in the case of groupoids, the working definition was that the graph of the multiplication was coisotropic. There was no, in principle, direct equation, like one single equation that gave this condition. So, so the first thing is that Mackenzie really understood a different way to express these compatibility conditions between the groupoid multiplication and the geometrical structure. And so here are a few facts that I'll just list. So the first fact, so let's suppose that we have a groupoid. Lie groupoid. So the first thing is that its tangent bundle is naturally a Lie groupoid again. Over what? Over the tangent bundle of the base manifold, and we just take tangent of everything. Tangent of the source, tangent of the target, tangent of the inversion, and everything works. More interestingly, and perhaps less obvious, is the fact that the cotangent bundle of a Lie groupoid is also a Lie groupoid. It's actually a symplectic groupoid. And in general, it's not of this action type. Because in general, you don't really have an action of the groupoid, some kind of a joint action. Right? And this groupoid is over, again, careful that it's not just playing with symbols, the dual of the Lie algebroid. Remember that for Lie groups, we had already seen that the action groupoid was over this space. Right? And an important observation is that a bivector field is multiplicative if and only if the corresponding bundle map from T star G to TG is a groupoid morphism. And the same is true for forms. So, and similarly, I'm going to write it here, that a form is multiplicative if and only if the corresponding map from TG to T star G is a morphism of groupoids. All right, so I won't need this anymore. So let me just all right. So on the other hand, if you have a Lie algebroid, then it's also true that you can lift somehow this algebroid structure to the tangent bundle of the algebroid and make it into an algebroid over Tm. And it's also true that you can do that. So they're both Lie algebroids. And in fact, there's a nice way to see why using Poisson geometry. So basically, using the fact that A star has a linear Poisson structure coming from A, and then taking the tangent lift and then dualizing things again. But anyway, I won't explain that. I'll just use this fact that these both are naturally Lie algebroids. And, and even nicer is the fact that the Lie algebroid of the tangent groupoid obviously should match this, and this should match this. Okay, so these are all observations that, in any case, took a while for people to understand. So let me now just sketch the proof of these results. So first of all, let's see, going from a Poisson manifold to a symplectic groupoid. So what is the key observation here? So, unlike what Rui was doing, he had a method that constructed the groupoid, using this path, right? But, I'm going to assume that I know what the source simply connected groupoid integrating the algebroid of the Poisson manifold is, and I'll just explain to you why this guy inherits a symplectic structure. Just this bit I'm doing. Okay, so I assume that the groupoid is there already for me. So why does it inherit a symplectic structure? And here the point is just that in this case A is T star of M with a certain algebroid structure, but T star of M is a symplectic manifold, so this has a canonical symplectic structure. I don't know, let's call it like this, right? So the canonical symplectic structure is a two-form on the total space of your algebroid. It's just there, right? And then the next thing you'll notice is just that if you look at this map associated with the form going from TA to T star A, you just immediately check that this is a morphism of Lie algebroids automatically, right? And now I can use the part of Lie theory that works well for algebroids, namely that if I know a groupoid integrating this, then I can lift morphisms, right? So a groupoid integrating this, from what I said there, is TG, and if this is the source simply connected one, TG is the source simply connected one integrating this. So then I can just lift this to a morphism like this, and that's the symplectic form on the groupoid. So, it's as simple as that. This observation is really, very fruitful somehow. So what about going from Lie bialgebroids to Poisson groupoids? It's just as simple. So now, what do we have? So now we have A star, and A star has a Lie algebroid structure, right? But remember that one way to see a Lie algebroid was to see it dually as a linear Poisson structure on the dual bundle. So the Lie algebroid structure here I can encode as a linear Poisson structure here on A, on the total space of A, right? So this Lie algebroid structure gives me a Poisson structure on A. And again, to a Poisson structure I have naturally a bundle map associated to it, right? And I haven't used the compatibility yet, right? So what is the compatibility? That formula that I wrote before. It exactly amounts to saying that this is a Lie algebroid morphism. It's exactly the same thing, right? Then again, I can just lift it to a map. I can integrate to a map from T star G to TG, which is nothing but the natural map associated with the bivector field that you're looking for. Okay, so this is really what this proofs, how these proofs go. Perhaps with some work to, set these things here straight. But but the integration itself is really this. It's just this. Okay. So what I want to do tomorrow is push this a little further and talk about multiplicative differential forms in general, and see what the infinitesimal counterparts of those are. And we'll see that it's related. You can find examples related to equivariant cohomology, to twisted Dirac structures, and to that will eventually relate to what Anton was talking about today, about constructing this nice two forms on G times G. So he needed these forms that were the analog of the cotangent bundle case, right? That were kind of the building block for this group valued moment map approach to the modular space of flat connections. These forms are related to this business. And that's what I hope to talk about tomorrow. So finish here. Thanks.